Okay, hello everyone. My name's Adrian MacKenzie, and I'd like to welcome you to the second day of Images and Machine Learning workshop. Okay, right now we're in the midst of a kind of production crisis relating to internet outages in southern Germany. And so although you're seeing me now, hopefully on the YouTube live stream, we're just at the moment kind of reconfiguring things because our keynote speaker, Fabian Offert, who is going to be speaking in a few minutes, has got an internet outage where he is locally. So we're going to rearrange the program this afternoon a little bit to accommodate that. And hopefully Fabian's internet will come back on sometime this afternoon. I'd like to begin, well, I'll tell you about the program in a minute, but I would like to begin by just acknowledging the country I stand on. I'm standing on the lands, the unceded lands of the Ngunnawal and Ngambri people here in Canberra in Australia. They're the traditional owners of this land, and sovereignty of this land was never ceded to, by them. I'd like to pay my respects to the elders, past, present and futures of these people, and also those of the lands on which you stand. I'd like to echo something that Anna said yesterday in her introductory remarks and acknowledgement. And she was saying that, you know, the very materiality of images, the images, in fact, that perhaps you're looking at now through your screens, is intricately wound up with the lands on which we stand. I think here in Australia of the rare earths that are being mined, have been mined, the silica that has been mined, these, you know, just in that literal sense, the very materiality of the images that are moving in front of you now are in some ways indebted to those lands, and in fact, the energies too that no doubt are animating what you're seeing come from those lands as well, whether they're renewable or non-renewable energies. So to update you on what we're planning to do this afternoon, we were due to begin with a keynote by Fabian Offert, and that was to be followed by a project launch, the ImageNet project, and followed by a panel on images, machine learning, and practices of knowledge production. To try and work with this outage, we're going to rearrange slightly and begin with the ImageNet project launch. That'll be Anna Munster, Kainan Tan, and myself talking about the ImageNet project. And then after that, if Fabian's still not available, we'll run the panel with 3 speakers and have a break after that, followed by the keynote. That's the current plan at the moment. Things may shift again, depending on how the platforms, the infrastructure, and all those things come together this afternoon. Our plan practically is to move across, to do a bit of live streaming now for the project launch, and then for the panel, move across to the Zoom link. Have I got that right, Anna and Kainan? Yep, okay. So I guess we'll shift to, well, introducing Anna Munster, who you met yesterday, Kainan Tan, and myself doing the project launch for ImageNet.
Hi. Okay, so I'm just going to share my screen with you so that you can join us in having a little bit of a look at, I suppose, the thought mesh behind the image mesh. And so just give me a second. Okay. So this symposium is in some ways a kind of celebration and a kind of one endpoint of a project that Adrian, Kainan and I have been working on for you know, the last, well, I guess 3.5 years really, perhaps even a little bit longer. We don't really count 2020, so we're not sure. We're not sure about that one. And Adrian had the idea that instead of sort of, you know, doing the rah, rah, rah thing about, you know, how wonderful this project is, which is wonderful, we should show you a little bit about what we kind of call the sort of set of kind of layer cakes and cream in the middle of everything, from going from a kind of project idea, which was really about this notion of sort of statistical visuality and the ways in which machine learning is configuring and reconfiguring images, and the ways in which images also reconfigure machine learning. And so this is a little excerpt from our ARC proposal, and you know, in that proposal, we sort of said that we would create a data set that was a kind of going to be able to track the ways in which ideas moved across sort of scientific domains, and then sort of out into kind of commercial spaces and into artistic spaces, and the ways in which, you know, ideas of statistics and its visual cultures and visual forms were really taken up. Now, actually, to my surprise, because often the things that you propose in a grant proposal don't get done, we actually managed to do this, but it was not at all linear. And in a way, you know, I want to sort of emphasize that there's a lot of mess in the middle when you think. And so, you know, one of the kind of big areas of research in machine learning at the moment with respect to images is the idea of kind of how is it that a model actually, you know, picks up on the features of an image and then produces a new sort of generative image or a synthetic image, or finds a way to predict or classify an image. And, you know, this area is called interpretability or explainability. So we thought we'd do a little bit of this in the area of kind of thinking, given that, you know, nobody really knows what thinking looks like either, although Philip gave it a good old try yesterday. So this was a meeting that Adrian and I had in 2018 in a place called Carlisle, which is, well, Adrian, where exactly is Carlisle?
On the border of England and Scotland, really.
Yeah.
Yeah.
So we kind of met on a border, and we met in a park actually, and had a really interesting conversation about what we might do with this project, and we kind of came up with this plan, which was kind of crazy. The idea was that we would download the whole of the archive repository. An archive is a preprint repository for scientific research papers. Started in 1991, and increasingly becoming the place where new research, particularly in the areas of computer vision, machine learning, and so on, is kind of previewed. Basically, we decided we were going to download all of ArchiveX, and then basically create a model that, by looking at the images of machine learning in the archive, would then predict where prediction was going. You want to say anything about that, Adrian?
Yeah, I mean, it was totally hyperbolic, kind of this aim. First of all, just dealing with all the papers from archive, and well, Anna Rither mentioned archive yesterday. It's been mentioned a couple of times in the workshop. It is a huge kind of mixture of disciplines, although machine learning research there, it's full of astrophysics and quantum physics and quantitative finance and quantitative biology. So it's a kind of epistemic kind of jungle in a way. It's just rich with stuff. So this is a hyperbolic kind of ambition to actually say, well, this preprint archive, the place in which the latest breaking techniques has been found, itself is going to become the site of prediction. People put things there because it moves much faster than the publication schedules of journals. And in a sense, I guess it was an ironic mode of approaching I mean, serious irony, but it was an ironic mode of working with what's happening with machine learning to say that we were going to build a predictor, well, we were going to try and model prediction itself. That's why in the previous slide, there's something called the infinite predictor, which was a play on Monica Moonham's infinite descriptor. I should point out, it was indebted to her project, the infinite descriptor. We talked about the infinite predictor. So ridiculous kind of over-promising. However, that is fairly common in the world of machine learning. So we weren't totally out of step in doing that.
And so this was the kind of like architecture, the thought architecture of the project. And this was sort of what Kynan worked with over the 2.5 years that he's been working on the project. And we basically call this a layer cake. Hasn't got a lot of depth, but then neither do many models either have a lot of depth. In fact, they just have lots and lots of surfaces and passes through those surfaces. So what I thought we'd do now is just kind of show you where this all ended up, which is a screenshot from this project ImageMesh, which we'd like to now launch. So I'll hand you over to Kynan, and basically he can step you through where we got to with this project.
Great, thanks Anna, thanks Adrian. So I'll just share my screen here, and let's check. Can you see that okay? Yep, I'm getting some nods, great. Okay, so this is the ImageMesh project. I'll just talk a little bit first about the data set. So Anna and Adrian have already mentioned that we were quite ambitious in that we wanted to work with the entire data set of archive, and particularly the images found within the bulk source data. So one of the things we set out to do was download and assemble this data set from which contains over 1.5 million ePrint articles and over 12 million images as of July 2020. And we went through a process of downloading this, extracting the images, and then converting the images, as well as creating a database for the metadata, so that data related to the images, related to the paper, and also related to the various experiments that we did with machine learning tools could all be linked together, and this huge repository of images could be queried and used to basically navigated and sliced up in different ways. We took a fairly recursive approach to running these experiments in that we spent a lot of time performing little experiments and learning about the data set. And I really loved when Anna Ridley yesterday was talking about how she needs to learn about the data set, like look at all of the images in the data set and get a real sense of what that contains, really this sort of understanding of what the data set is about. And we found that we had to do a number of different experiments to sort of get a grip on what was actually in this data set of 12 million images. And so we would do this recursive project or process of learning about the data set and then reconfiguring how the data set was organized. And so through this process, we ran a number of experiments, including manually looking at the images, first of all, but then also using TSNE and UMAP as unsupervised clustering techniques, running image classifiers over the data set, manually labeling images and then training classifiers using that, and using machine learning tools to slice the data set in various ways, and observing how these different ways of looking at the data set could be measured in terms of similarity. So I'll give a little demo of what ImageMesh here is what this project actually shows and does. So this is the homepage of ImageMesh. I'm going to try showing it on the live website. Hopefully it can handle the load if other people are using it at the same time. We'll see how the infrastructure holds up. But as you can see, this is the homepage. It brings up a number of randomized images from the data set. And for each of these images, we can click on the image and view the metadata. So the paper that the image is associated with, we have the identifier, which also links to the archive paper, the date, the category or subject area, the authors, and the title. We also have some data about the image file itself and the caption, where the image was located, which figure the image was located in the paper, what the caption was for that figure. I can then click again on the image, and this selects the image to be used for a nearest neighbor search. So right now I have nearest neighbor search selected with the ternary machine learning embedding. And so if I click on search images there, this brings up a selection of images ordered by how close they are to the selected image, ordered by this ternary classifier. So in this case, the ternary classifier is a model that we trained on this data set to predict whether images were diagrams, sensor generated, or diagram sensor hybrids. I can then change this prediction to VGG16, which is a model trained on ImageNet. And if I run the search again, it will give us quite different results. I'm just going to jump back to the home page and run this again on a different image for a bit of a different example. So for example, maybe I can use this image here and then search using that and finding the nearest neighbors to that image. So with this platform, we can also do a keyword search. For example, I can search by convolution, which will then only select images that have the keyword convolution somewhere in the metadata. And you can see here that brings up a total of 3,742 images. I should also mention that this version of the of ImageMesh uses a subset of the total number of images. So rather than using a full 12 million, it uses 600,000 images drawn from that data set. So I guess I just want to show a couple more things that ImageMesh can do. Firstly, we can limit the search by archive and category, which, for example, I can use computer science and computer vision and pattern recognition, and that further limits the search and provides a different slice of the data set. There are a number of additional filters here that can also be used. One example of that we can use is the VGG prediction. So we can also see what the VGG classifier predicts the image as. So in this case, it's predicting this image is an oscilloscope. And I can use this drop down to actually search only by images that also match oscilloscope. So this is a total of 77 images now that match these various search terms. One other thing I'd like to show, I'm just going to clear all those filters and just demonstrate the difference between some of the machine learning embeddings. So this is using the ternary embedding, which, as I explained, is a classifier we trained. If I compare that to the VGG16, it will bring up a different set of images. I can also compare that to, for example, deep cluster. So this was another network that we trained. It uses unsupervised learning to cluster the images into 100 different categories. And those categories or clusters are emerge from the data set. They weren't predefined. And so this will, again, bring up quite different results. And essentially, I think what is interesting here about ImageMesh is that it enables us to use the images themselves to access and also navigate different slices of this data set that are influenced by the machine learning techniques. Okay, I might pass that back to Anna or Adrian if you have anything that you'd like to add to that.
Thanks a lot, Kynan. So I guess, you know, what we wanted to sort of say was there's sorts of interesting recursions and kind of novel relations that you might see when you play with this project online. Also actually occurred when we were thinking about the project as well. So I guess, you know, it's been a very interesting experiment in thinking and making alongside machine learning and what that might mean. So we'd be very interested to get feedback from you. Please email us and let us know how you think the application is going, whether you're enjoying it, that kind of thing. Even have a look at it now and have a play, and we might, you know, be able to have a chat about it in the panel. So speaking of which, handing over to Adrian now. Okay.
Hi, everyone again. We're getting back on track a little bit. If you're just joining us now, we're just about to start our first keynote for this afternoon with Dr. Fabian Offert. I'm going to introduce him a little bit and then hand over to Fabian. I'm hoping that we have time, 15-20 minutes for questions towards the end of this session. Fabian's based at the moment he's in Nuremberg, but he's based institutionally in the University of California at Santa Barbara in Germanic and Slavic studies, as you can see from his web page. It's interesting that you know, comparative literature departments have been particularly I guess, active in intensifying engagement with digital technologies. And Fabian's work is definitely part of that. He's in the kind of area of digital computational humanities. What's distinctive about his work, and I find particularly interesting, is that his work is definitely positioned within the kind of emerging apparatuses of working with visual culture and also actually audio visual culture and language more generally. And although his work is quite critical, it has a kind of archaeological aspect to it. It also practically inhabits the apparatus. He's not standing back outside machine learning and kind of observing things like bias. He's actively working within particular techniques and architectures and trying to expand our understandings of what's at stake in them. I see in his work kind of an attentiveness to architectures, materialities. For instance, he's written recently on the challenges curation and archiving of hardware configurations. But he's also working at a kind of quite abstract or conceptual level around notions of perception and bias. A recent piece is about how we think about bias in machine vision, beyond or perhaps in parallel to the very high profile critiques of bias in data.
By courtesy of my neighbors from downstairs, whose internet I'm currently using. So I hope everything will work from here. So I'm very sorry about that. All right, let's get started. So my slides will be in my speaker window. So I hope this will still work, and it should. All right. So first of all, thank you, Adrian and Anna, and also Kynan and Charo for organizing this. I'm very happy to be here to be speaking today about latent deep space GANs between art and science. We've heard a little bit about GANs yesterday already in Anna's keynote, and I will try to dive a little bit deeper into the technical side of things, specifically into the use of GANs in the sciences. So in late October 2020, so basically in the middle of the global pandemic that we had, the Turing Institute, which is Great Britain's most important computer science research institute, announced a new project with the remarkable title, AI for Scientific Discovery, Developing Artificial Intelligence Systems Capable of Noble Quality Discoveries by 2050. This is their website, and if you scroll down, you'll see that one of their goals is to create a landscaping study for AI systems that have highly autonomous capabilities to perform scientific research. And as with all things AI, it's important to consider here the economic and political interests behind such a claim, particularly where it reaches this far into a quite uncertain future. But while this kind of automated noble quality research may remain unattainable for a time at least, machine learning for science has come a long way since the beginning of the current AI summer, we could say, around 2012. Most recently, a machine learning system by Google's DeepMind AI Research Center seems to have solved, in quotes, protein folding in biology, at least within the constraints of a kind of formalized assessment of the quality of such systems. At the same time, researchers in physics have started to utilize machine learning systems to discover and rediscover physical laws or directly derive symbolic representations from observations, from pixels to physics, basically. And this is one of my favorite examples, Hamiltonian neural networks. And this is a system that directly learns energy conservation laws from raw video footage, basically. And at the same time, critical research on AI in media studies, visual studies, and well, the kind of like still forming discipline of critical AI studies in the past 5 years at least has focused mostly on either the history of artificial intelligence, for instance, its relation to cybernetics, or on its contemporary socio-political use. And while of course the significant individual and societal harms of applications like face recognition and predictive policing have warranted and still warrant this kind of attention, this somewhat narrowed focus has produced a kind of backlog of technical reality. And this is just a list of GAN architectures, and it just goes from A to C. So you can imagine the list continues from there. And I'm showing this because among the architectures that make up this technical backlog, and there are many of them, this is something that we would like to investigate in a new small research group that we're forming at UCSB called Critical Machine Learning Studies. Among them, one warrants particular attention, I think, from the perspective of media studies and visual studies, the generative adversarial network, the GAN. While GANs have been studied in the context of, for instance, deepfake, so again, a political context, and also as Anna Riddler has demonstrated impressively yesterday as a creative tool, their distinctive role in the sciences, so in astronomy, in medicine, in chemistry, and biology, among other disciplines, has gone largely unnoticed. So what can we say about the use of GANs in these fields? My main hypothesis for today is very simple, and it's this: in the sciences, GANs pass as optical media. But while they seem to enhance our view of an object under investigation, be it galaxies, cancer cells, brainwaves, these are all things that we'll look at in a little bit, they actually present us with a technically and historically predetermined space of visual possibilities. In short, what there is to know is what is already known. What there is to see has already been seen. And this is what I'd like to try to show or illustrate in the next few minutes. And as hinted at in the title, we'll start from space and work our way down from there. As Peter Gallison, historian of science, reminds us, we desperately need images to make sense of the world. At the same time, we fall so easily for their, quote, siren call of material specificity. As objects in the world, their simple presence often obfuscates their inadequacy as vehicles of representation. We should not rely on them too much or hope they would speak the truth. At the same time, of course, without images, we cannot proceed further towards abstraction, simply because we cannot think in purely symbolic operations. And this dialectic of the image, this is Galson's historical argument, then materializes as what he calls battle between iconoclasm and iconophilia in 20th century science. In other words, the image, and the scientific image in particular, is unstable. It oscillates. It wants, to invoke W.J.T. Mitchell here, it wants to be two things at once. It wants to be the concrete material object under investigation, and it wants to be its abstract symbolic representation, and yet it is neither. This kind of epistemic oscillation of the scientific image generally concerns both analog and digital images. But for Galison, the computer has rendered what he calls flickering exchanges between the abstract and the pictorial more pronounced. The frequency of the oscillation is increased as computation enables images to, quote, easily scatter into data and data to gather into images. This is a paper title from Galison as well. But no matter how frictionless the computer renders this oscillation, we have to keep in mind that every phase change requires, in image terms, a kind of lossy conversion, right? So a violent representation of reality, as Klaus Piers calls it. Every time images gather into data or data gather into images, 1,000 human decisions come into play. And more importantly, for our investigation of GANs, the image itself conceals these human decisions. If at all, they can only be recovered through forensic words. In other words, a fundamental epistemic opacity is created here in these images. The famous black hole image from 2019 is a good example for this dilemma. The image's only reason to exist is to give evidence to the symbolic equations that describe the phenomenon it represents. It exists on the threshold to the non-image as a last glimpse of what is pictorially possible. It represents, as Ort Halpern has put it, the figure of the terminal limits of human perception, or as Galison writes, at the end of images scatter into data, data gather into images. General relativity gives a fascinating description of an object falling into a black hole. As the object approaches the event's horizon, the point of no return, an outside observer sees that object slow down as it approaches the horizon, its image gradually shifting towards the red. Eventually, the scene of the falling object freezes in dimming redness at just the instant it passes beyond the visible. That scene resembles ours. Just when the scientific image moves towards abstraction, we are left with the last glimpse of a frozen picture and ignore what happens next. The black hole image can only exist because computation enables data to gather into images, the actual photographic process involving terabytes of data being rearranged. The epistemic opacity at play here becomes particularly obvious if we consider that we can also easily approach this task of creating a black hole image, basically from the other side of the material to symbolic continuum, for instance, with a physically based rendering system that allows us to precisely compute the scattering of light for arbitrary objects. This is exactly what was done for the movie Interstellar, that many of you will know, that shows a black hole and that precedes actually the 2019 photograph that I just showed. While, as Jacob Gabery has pointed out, even physically based rendering has to make significant compromises to arrive at realistic results, one thing is kind of obvious. Between such two images, intuitively, there would be no way to tell which is which. Not because of sophisticated photo manipulation or 3D rendering techniques, but because both images would represent or do represent a phenomenon at the threshold of what can be depicted in the first place, where quite literally on the event horizon, the light that would give birth to an image is stopped in its tracks. Or to quote Ort Halpern again, the borderlands of perception require, quote, a turn to automation and big data as modes of managing extreme uncertainty. And it's exactly there where GANs start to become relevant. So I will keep my discussion of the technical side here quite short, because on the one hand, I'm sure that most of you will be familiar with the kind of basic principles of GANs, and also we've heard about them from Anna yesterday. So very briefly, GANs leverage game theory to approximate the probability distribution that defines a set of images. And this is done by a kind of a game between two different neural networks, a generator network and a discriminator network. And basically the generator takes a number, a vector from a latent space, turns this into an image, and the discriminator tries to decide if this image, or the discriminator tries to decide if the image that it's looking at comes from the generator or from a batch of real samples. Both are trained together, so at the end you'll get a generator network that has learned to produce images that look like they come out of a data set, the data set of real samples, but not quite. So in the best case, it learns the kind of image, the style of image that is contained in the data set. Or with Gallison again, we could say data, Z, this is the latent vector, gather, that is what the generator does, into images. This is the image that the generator produces, and images scatter via the discriminator into data. And this is the judgment the discriminator gives for the generated image. So we could read GANs with this kind of like basic theory of scientific images. And importantly, this also means that the high frequency epistemic oscillation of digital images and of scientific images that I talked about is a defining feature, or could be seen as a defining feature of GANs. Now, current generation GANs, like StyleGAN2, are able to produce extremely realistic samples from large image corpora. On my left here, this is one of the most prominent recent deepfakes, Deep Tom Cruise. So you can find that on TikTok, and it's indistinguishable from the real actor. It involves not only GANs, but also a mix of other techniques, good Photoshop skills and things like that. But it demonstrates what can be done if care is taken with GANs at the moment. And there's countless other examples of GAN-generated images that you can find on the web. For instance, one of the best sites to explore this is thispersondoesnotexist.com, which allows you to generate these imaginary portraits, or rather portraits of imaginary people. You can just refresh the website and then you get a new AI generated person every time. But now, given that we are looking at GANs in the sciences, what kind of problem could such a system potentially solve? What kind of scientific application does a system have that has learned to imitate a certain kind of image, or more precisely, that has learned the defining features of a certain set of images and is able to construct new samples from this information? And as it turns out, these exact properties come in handy in the approximation of a certain class of scientific problems called inverse problems. Inverse problems commonly emerge in science where it deals with objects that need to be observed, but that are somehow out of reach. So in astronomy, which is concerned with objects that are often millions of light years away, trying to obtain something like a clear view of an object commonly becomes an inverse problem. And importantly, it becomes an inverse problem with solutions that are impossible to verify. To further complicate things, with the invention of more and more elaborate optical media, the most important inverse problem in astronomy has become the reconstruction of images that have been perturbed by noise produced by the very instruments that facilitate the imaging, right? So you have better telescopes, and these telescopes introduce a specific kind of noise into the observation. And just as an illustration, this is different photographs of Pluto over the years. And you can see we got better and better. But of course, this means we got different kinds of noise with these improved imaging techniques. So signal and noise in these observations are hopelessly entangled often. So disentangling signal and noise becomes a difficult nonlinear exercise. And this is an area where artificial neural networks are traditionally good at. It's where they excel. One example from a recent paper is the denoising of images of galaxies. So this is from a paper called, this is a very long title, Generative Adversarial Networks Recover Features in Astrophysical Images of Galaxies Beyond the Deconvolution Limit. And in the paper, the authors describe a technique that's based on a GAN architecture called pix-to-pix, which is a conditional image translation technique. And what they're trying to do is they're trying to reconstruct images of galaxies that have been perturbed by, this is a quote from the paper, various sources of random and systematic noise from the sky background, the optical system of the telescope, and the detector used to record the data. And the reconstructions facilitated by the technique that they call galaxy GAN, by the way, transcends the deconvolution limit according to the author's claims. Now, the deconvolution limit is kind of a hard limit. It sets a lower bound for all kinds of digital reconstructive techniques, not only in the image domain, but in all of signal processing. And it's based on the Shannon-Nyquist sampling theorem. And basically all it says is there's a limit to what is naturally reconstructible from a limited amount of information. So this is a hard limit. And transcending this limit accordingly has for a decade been a kind of goal and also a topic in science fiction. And the most prominent example here is, of course, Blade Runner, where Harrison Ford gives voice commands to a computer system to almost infinitely enhance an image. And from there, basically, this topic of enhancing an image infinitely, reconstructing details that can't be seen, has become almost an internet meme. So with shows like Navy CIS, I don't know if you're familiar with that show, in the meantime, like intentionally exploiting the ridiculousness of these infinite enhancements. So it seems there must be some sort of catch to these reconstruction techniques that attempt or claim to transcend the limit of what is reconstructible, to transcend the deconvolution limit. And indeed, at the very end of the paper, the Galaxy paper, the authors point to some important limitations. Quote, in general, the GAN fails on rare objects that were absent or low in number in the training set, stressing that the performance of our method is strongly tied to the training set. It cannot reconstruct features it has not learned to recognize. And intuitively, this seems like an expected limitation, right? GANs cannot reproduce what they have not seen. That is seen at least once in theory and actually seen a significant number of times in practice. And as has become quite clear in the past few years, this technical limitation quickly turns into a socio-political problem as well. So this is another example of a reconstructive technique using GANs that became kind of viral on Twitter. This is a face upscaling algorithm called Pulse. It also uses GANs. And the example below me here of the upscaled Obama that became a white, kind of like run-of-the-mill white guy, made the rounds on Twitter and shows that what the GAN is doing here is basically imagining details based on the training set, which obviously had some flaws that was biased towards a certain skin tone. Now, to be clear, this is a widely acknowledged issue when it comes to inverse problems. But, and this is the crucial difference, GANs, if they're used, fail silently. The solution space facilitated by a GAN is what we could call a dense solution space. There's always a solution, as the generator has learned a mapping from all possible inputs to all possible outputs. GANs always give coherent answers, even if the question is ill-posed, like here in this example. While regular noise is an obvious perturbation, when it is removed by a GAN, it is secretly, we could say, replaced by the epistemic priors inherent in its latent space. the fact that the image remains perturbed, only in a different way, is concealed in the image. So while it does seem that GANs provide the clear image that we desire, what we get is an image that pretends to be clear while being fully dependent on a set of epistemic priors. GANs, in a peculiar way, thus operationalize the epistemological distinction between invention and discovery by rendering the space of discovery a technically determined space. And importantly, this determination is a historical determination, where GANs serve as a medium. What there is to know is what is already known. GANs thus not only amplify the frequency of the epistemic oscillation of digital scientific images in the sciences, but they also amplify their potential to conceal the human decisions involved in the high frequency back and forth between image and data. While the black hole images conceal only the specific technical process necessary to produce them, GAN-facilitated images can and do conceal whole corpora of images. Now, so far, these problematic implications of GANs seem to have emerged from the unavailability of the objects under investigation. We talked about black holes, galaxies, and things like that. And we could argue, about black holes, galaxies, and things like that. But in fact, we do not have to venture into space to see these implications at work. We can focus on humans instead, human bodies instead of celestial bodies, because in recent years, GANs have become human-centered, to intentionally reframe this technical term, and have found their way into the medical field. And the example you see here is from a large-scale data set of MRI images that is freely available. In a recent paper called Distribution Matching Losses Can Hallucinate Features in Medical Image Translation, the authors describe a system based on cycle GAN, a GAN-based approach to unpaired image-to-image translation. Other than pix-to-pix, so this is the model that was used on the galaxy images, cycle GAN does not require pairs of images, so examples of original and then degraded images, but simply two data sets of images from the two translation domains. In medical imaging, where image making is complex and expensive, attempts have been made to employ such techniques to translate between different variations, different kinds of imaging techniques, for instance, so-called FLAIR and T1 MRI images. So these are just two MRI imaging techniques. And what the authors in this paper show is that if the training sets from both domains are only slightly unbalanced, for instance, if there are too many or too few images of cancerous tissue in one of the data sets, cycle GAN hallucinates features in the translated image. As the authors state, they, quote, demonstrate the problem with the caricature example where we cure cancer in images and cause cancer in images using a cycle GAN that translates between FLAIR and T1 MRI samples. Moreover, in a thorough analysis of the amount of difference needed to induce such hallucinations, they show that the imbalance in the data set has not to be total. So you don't have to have one data set with only cancerous tissue and one set with healthy tissue. But there is a threshold where feature different samples become irrelevant to the GAN. So just to summarize this briefly, you just want to translate between two styles of images, basically, two different kinds of images. And what you get is you get a complete, change of the content of the semantic aspects of the images as well, because the cycle GAN hallucinates these features because it doesn't know any better, basically. And we can take this even further, and or to put this differently, researchers, scientists have taken this even further and look at human brains. In a paper called Deep Image Reconstruction from Human Brain Activity, the authors describe a machine learning system to quite literally make sense of MRI data. The training set consists of images and the brainwave responses of test subjects in an MRI machine looking at these images. So there's basically a person in an MRI machine, you show them an image and you record the MRI data in a certain part of the brain. And then you have one data set with images shown and one data set with the response, the participant response. Once trained, the network produces images from unseen MRI data, providing a visual approximation of a test subject's imagination. But where do these images actually come from? And this is the crucial point. They come from a GAN latent space. More technically, they are produced by utilizing a technique called feature visualization with natural image priors. This is something I've written about in a recent paper, which in turn uses a GAN latent space as search space to find the closest visual match for a targeted image. So the way this works is actually quite straightforward. Instead of optimizing an image in pixel space, so you want to visualize something, if you could optimize all the pixels, you just optimize the latent code, the latent vector of a pre-trained GAN and create the image like that. This is why the GAN is relevant here. While the authors also run the experiment without using GAN images as natural image priors, so without conditioning the optimization, conditioning the search with the GAN, interpretable images, so images that show something in the literal sense of an identifiable object, something, depend on the use of a GAN. Without it, the images that can be reconstructed barely resemble the forms seen or imagined by the person in the MRI machine. While the reconstructions, this is a quote, while the reconstructions obtained without the deep generator network, the GAN, also successfully reconstructed rough silhouettes of dominant objects, they did not show semantically meaningful appearance. Quote end. In other words, meaningfulness itself is necessarily restricted, again, to the latent space of the GAN. Moreover, the images seen by the study participants in the MRI machine come from the ImageNet Dataset. This means that it's even easier for the GAN, which has also been trained at ImageNet, to produce almost perfect reconstructions, as it has been trained on the same dataset that the images it is reconstructing are taken from. Moreover, as a pre-trained generator from another technical paper is reused instead of training a new generator on a subset of ImageNet, omitting the test images, the generator necessarily, quote unquote, knows the test images already, albeit only through their contribution to the learned probability distribution. Whatever the person in the MRI machine is thus imagining, it is expressed in terms of the legacy GAN. This is kind of the takeaway from this, right? So through all this procedure, the person in the MRI machine can only think within the GAN latent space of the pre-trained GAN, trained on ImageNet. So it's artificially constrained, of course. Oops. Pardon me, I lost the slide. There it is. Given these examples, one could rightfully ask if GANs can ever have a place in science at all, if their incredible potential to conceal is not fundamentally opposed to scientific principles. At the end of the day, all GAN images are deepfakes, images designed to deceive. One could argue then that the only real benefit of GANs is exactly their tendency to capture and distort in interesting ways what is already known. And the fact that the black hole image has been acquired by the Museum of Modern Art in New York already speaks of this aesthetic potential. And more recently, contemporary artists working with artificial intelligence have explicitly turned to GAN images in the sciences to generate speculative environments. Oops. French artist Pierre Yuri, for instance, utilized the methods described in the brainwave visualization or brain MRI visualization paper that I just talked about in a 2019 exhibition to create images. And this was a show called Umwelt, originally shown at Serpentine Gallery. and then we exhibit it in a 2021 online version on a different title called Off-IGO. The images were created in collaboration with the Kamitani lab at Kyoto University, where the original paper was coming from, originated. In the original exhibition space, the images are presented as video loops that capture the optimization process, so the latent space search of the GAN system, juxtaposed with 100,000 flies occupying the gallery space. Temperature, humidity, smell, and sound are also controlled elements in this hybrid digital organic environment, mirroring previous works by Yui, like After a Life Ahead at Skulpturenprojekte Munster in 2017, which was a fantastic project in an old ice skating rink where some more of these flies lived and other things were going on. The gallery becomes, quote, a porous and contingent environment, housing different forms of cognition, emerging intelligence, biological reproduction, and instinctual behaviors. And it is through these organic elements, of course, that the exhibition emphasizes the distorted nature of the reconstructions shown and their inadequacy as representations of thought. My final example is Tiger Brain's installation, Asunder. Asunder is a 3-channel video installation that speculates on the potentiality of climate interventions. In the installation, a neural network is used that has learned to generate imaginary satellite images according to certain parameters. Real-life satellite images are changed by this network to suggest radical geoengineering interventions. So removing the city of San Francisco, planting trees in the desert, rerouting whole rivers, lakes, and so on. The resulting composite image is then fed into a scientific climate model, which runs on a high-performance computer in the exhibition space. And the resulting changes in the global climate are displayed. And I think this work is particularly relevant to the hypothesis that I just proposed, because it puts the peculiar epistemic implications of GANs on their feet. The literal alienated perspective of machine learning systems is transformed into a productive alienation in the Brechtian sense, right? A distancing from the matter at hand with technical means. The speculative nature of inverse problems is embraced and utilized to project the ridiculous exit strategies that humankind still has left. All right. And that was it. Thank you so much. And I really look forward to our conversation in the Q&A.
Thanks very much, Fabian. That was fantastic. Super interesting. What we're going to do now is gather some questions coming through the live stream channel. And like yesterday, I will kind of basically drip feed those through to you.
Okay, sounds good.
As they appear to me in the chat. It'll take a little while for them to come through because they've been kind of forwarded from the YouTube channel into my Zoom chat. So could you tell me, I'm just going to start off some questions while we wait for the audience to gather their thoughts. Do you think that the fundamental problem of GANs is that they can only see what has already been seen in the training data? Is that the kind of the fundamental limitations here, that GANs effectively reproduce what they saw in the training data?
Yeah, I think this is the one half of the problem. I think the other half, which has not been looked at so much, is that this is concealed, right? So that the fact, not only the fact that this is that this is a system that is epistemically limited to a certain set of images, but also which images they are, right, is concealed. So we have a system there that is really predetermined, fully predetermined, completely dependent on a very specific, concrete set of images, right? Only these images, and you can only get one specific GAN from one specific set of images. But not only the fact that it is dependent on these images, but also what they are is concealed if you have the system, and there's no way basically of reconstructing the original set from a trained GAN. So if you don't have them, you will never know what went into the generator, which of course then becomes even more problematic if we talk about pre-trained models, and specifically if we talk about pre-trained models that are used uncritically in other applications, right? Like in the brainwave brain MRI example, where they literally took just like one generator they had lying around from another technical paper that introduced the technique that they were using that was trained on ImageNet. So you get like ImageNet through the back door, and everything you do with the system is kind of like primed on ImageNet, but it's nowhere to be seen. It's invisible in the actual process.
Yeah. Do you think, sorry, I have the luxury of asking follow-up questions because I'm just waiting for stuff to come through. I mean, the fact that these networks, in fact, machine learning techniques are so rapidly taken up by scientists, that's evident in what you say. You gave us great examples of that moving across between astrophysics and, say, neurobiology. Obviously, we encounter that stuff. We see the announcements of that on the cover of Nature or something like that, or in the news. At the same time, we have the other world, not the other world, the somewhat distant world of social media, the world of deepfakes, of the whole flow of images. Perhaps what Katrina Sluice was talking about yesterday, the tsunami of images of the amateur photographers, or the deepfakes, what's happening on TikTok or YouTube. And they kind of share sometimes they even share the same platforms, but they definitely share techniques. There's a kind of constant oscillation between the ways in which the scientists are picking up techniques and mobilizing them on their image flows or their data, and the way the platforms or various other actors are picking up the techniques and feed them into, say, popular culture or media cultures. How do you think about the relation between those two? I mean, I'm asking because partly we did so much work on the archive images, the images from the physics preprint archives, and saw many of the kinds of images that that you were showing. But we're constantly aware that all of this is kind of resonating or strongly kind of, perhaps there's interference as well, coming constantly from what's happening in other areas of visual culture where the same techniques, the same devices, sometimes the same platforms are being used. How do you think about the relation between those two, the epistemic through to the media spectacle?
Yeah, that's a great question. I'd have to think about it more, I think. But I mean, the one chance basically I see in this sharing of techniques is, or let's say in the availability of the techniques being used in the sciences, being available to us as media scholars and image scholars, but also for, let's say, applications in, for instance, digital art history, which is a field I've worked in, to sort through large image corpora. I think one potential that this offers is to use them more critically, basically, right? To not only use them as tools to get to a desired result, but to integrate some sort of critical reflection into the tool use in the sense of maybe what Phil Ager calls a critical technical practice, where you use tools to do a thing, and then the tool building and tool using process not only informs your result, but also informs a better tool eventually at the end of the day, right? Kind of like loops back into the technical process as well. So that would be the potential that I would see in this intersection or sharing of tools. Maybe, yeah. Does that answer your question? Probably not.
Yeah, no, that's great to think about more. Yeah. Okay, my eyes are now moving over to what's coming through on the question channels. And I've got one here from Katrina Sluice. So your presentation strikes to the heart of the contemporary imaging systems where the output seems historically, culturally continuous, yet older tools and methods fail to read and decode their output. As these images proliferate and are naturalized, how do models of visual literacy need to change, especially thinking about public culture?
Yeah, that's a great question. Thanks, Katrina. And where did we see this? In Anna Riddler's keynote yesterday, Anna showed this handy chart where, how to detect GAN-generated faces. You can look at the ears that are sometimes off. They often don't get hats and things like that, accessories and things like that. So this is, I think, one example. And Colin McDonald, the artist, had a great essay. I think it's still online, and he updates it regularly on how to detect fake GAN-generated images. So I think this is definitely something that this is definitely also a visual literacy problem. But the more difficult one, I think, that results from all of this, and this is something that Georgina also mentioned in the talk yesterday, or talked about in the presentation, is that there's a certain consolidation of aesthetic principles, maybe. So one example that I'm thinking of is the recent CLIP network, which was released by OpenAI. So CLIP translates words into images. So actually it translates images into words. So you give it an image and it tells you what it is. But you can also reverse this and generate images if you couple it with GANs to create images from scene descriptions, basically. And there's many great works of art popping up all over Twitter and the internet using these and exploring these systems. But what you can see if you look at them carefully is that because CLIP has been trained on a data set that basically is, all the internet almost. It's the equivalent of this textual data set called the pile, which is basically just all the text you can get. And there's OpenAI has a similar data set for images. And what you can see is that the generated images produced by the system, if you do a Google image search for them, you'll find millions of similar images because they conform to a certain stock photo aesthetics. And every time a model is trained and the data kind of coagulates in the model, these dominant aesthetics, excuse me, are reinforced, right? Because then these models generate images that look like the input image or the input image data set, and you get more images, those go on the internet and the cycle continues. So there's a strange kind of like reinforcement of already dominant aesthetic principles there going on. And I think it's still an open question how to disrupt this, or if it's even possible to disrupt this, or if you even want that.
Yeah, great. I've got a question from Anna, which is, do you think GANs might take up a space within science as speculative imaging machines rather than as accessing ground truth? Imaging in science might, imaging in science in which prognosis is speculated, for example.
Yeah, this is a great question. Thank you. The reason why I showed Tigar Brain's example at the end is because this is what I imagine science should be like, right? This is an art project, obviously. But I think this is maybe one of the applications where GANs can be really useful in the sciences without having this big problem of concealment and this problem of imagining details that are not there and all these things. So but I mean, I'm not a scientist, so I feel scientists should think about that more, probably, how to use these systems beyond these reconstructive techniques, which have shown time and again that they are problematic and don't work and have all these biases. And one example that I think is interesting because it's productive in a different way, if we go back to the galaxies. So there's one paper that basically uses GAN-generated images of galaxies. So they train a GAN on galaxy images and then produce millions more, not to find something out about the galaxies themselves or have these images as kind of like the material for an analysis, but to calibrate telescopes for redshift, I think. And this is where this becomes useful because it's expensive and difficult to take so much images or so many images. But if you just use them to calibrate things, then if they're fake, it doesn't matter as long as they have the same properties. If they adhere to this probability distribution. So this is like a real life example that I can think of, but I can't think of any others.
Yeah, interesting. Question from Baden Palethorpe. Do you think we should accept the perceptual limitations of GANs as their own perceptual worlds, as for instance in von Uexküll's notion of Umwelt, and then work within those limitations?
Yeah, thanks. Good question. I mean, what would it mean to accept these perceptual limitations? This is something that I've encountered more, I think, in my other work on visualization techniques. So in one paper about feature visualizations, we talk about these things called, or these problems called shortcuts, where deep convolutional neural networks classify things based on surprising features of the image. The most prominent example, most popular example is, you train a network to detect cows, and then suddenly it stops working when there's a cow on a beach, because it has actually learned that, cows are always on green pastures and not on the beach. So, and once something surprising comes up, these systems fail. And these are called, in the literature, called shortcuts. And there's many more. One is a weird preference for texture over shape. So if there's same amounts of textural and shape information in an image, the network will always prefer the texture and use that for classification. And I think one potential of this might be that we might be able to question our own way of classifying images, looking at these machinic classifications. Right, so if we have the task of analyzing and classifying a certain image, we could look at machines and look at how they do it, and then see how these two modes of analysis can inform each other. Maybe in general, I think this is a problem not restricted to GANs. Actually, it's a problem of vision machines in general.
Yeah, that's great. Okay, I can't see anything new coming up in the top chat. So maybe at this point we should close this part of this afternoon's proceedings. I would like to thank Fabian very much for a totally interesting paper, and
thank you.
Yeah, both in its concreteness and also in the bigger ideas there. I particularly like the way your image seemed to change shape in the course of the presentation. At one point, how did you become regular Offert? That was interesting.
Oh yeah, that's regular resolution. Yeah, that's a
regular resolution.
The one joke I allow
Okay,
myself.
that's great. Thank you. I was interested in how you managed to do that, but I'll ask you at some point. Right. Applause doesn't really work. We're in the live stream. I'm sorry, but I'm clapping, and I can see hand claps coming up in the chat as well, but you don't get to hear it. Okay, thanks very much.
Thank you so much, Adrian.